A modern food delivery platform operates as a real-time coordination engine. It must synchronize three independent actors: the customer, the restaurant, and the courier, binding them together through a single order state machine. But virtual logic constantly collides with physical reality. An algorithm assumes constant velocity, but physical couriers navigate gridlocked streets, unpredictable weather, and road closures. On the merchant side, the system has to account for highly variable kitchen capacities, where a sudden influx of orders can paralyze a prep line and render algorithmic pickup estimates useless. At any given second, the platform coordinates 50 million active users, 500,000 restaurants, and 200,000 couriers, transmitting location telemetry. This forces a conflict between two opposing data patterns. The system must enforce strict ACID compliance for financial transactions, while simultaneously ingesting an avalanche of ephemeral location telemetry without the overhead of traditional disk-based writes. To see how engineers balance this, we will trace the lifecycle of a single order and map the decoupled microservice architecture built to support it. Building a planetary-scale delivery network requires distributed systems that can withstand the friction of the physical world. The technical challenge begins the moment a user opens the app. Before showing a single menu, the system filters out locations with paused kitchen capacities, closed operating hours, and mismatched delivery polygons. Running traditional geospatial queries across a relational database for millions of users simultaneously would take seconds per request. Users expect a fully populated feed in under 200 milliseconds. This map shows the solution. The globe is divided into an H3 hexagonal grid. By mathematically bucketing geographic areas into hexes, the system converts complex spatial geometry into simple string lookups. To find nearby restaurants, the backend executes a K-ring query. It takes the user's current hexagon and instantly retrieves all active merchant nodes from the 6 immediately adjacent neighbors. That pre-filtered list of location-valid candidates is then passed into an Elasticsearch cluster. Here, the list is resorted using machine learning weights based on cuisine preferences, historical prep times, and user ratings. Offloading these read-heavy discovery queries to specialized spatial indices and search clusters protects the core transactional databases from the volume of user browsing. Once a user builds a cart and hits checkout, the request routes to the order service. Here, a PostgreSQL database ensures transactional consistency so that a user is never double-charged and an order is never lost. This flowchart models the order lifecycle as a strict finite state machine. Every delivery moves sequentially through specific states: created, confirmed, preparing, assigned, picked up, and delivered. If the order service attempted to synchronously trigger notifications, payment processing, and dispatch algorithms directly, a single slow downstream service would stall the entire checkout process. Instead, the architecture uses an Apache Kafka event bus. The order service writes the state change to Postgres and then publishes an immutable event onto a Kafka topic. Downstream systems, like dispatch and notifications, process the stream asynchronously. They consume the event at their own optimal speeds, without requiring the order service to wait for a response. During a dinner rush, this decoupled event choreography isolates the payment database from the computational demands of matching drivers to orders. While the order service manages state, the platform is simultaneously handling its most intense write-heavy workload, ingesting location pings from 200,000 active couriers every few seconds. Every few seconds, thousands of GPS pings hit the platform's API gateway. Writing 50,000 location pings per second directly to a durable, disk-based database would cause immediate lock contention, resulting in a system-wide failure. Instead, the load balancer routes this data to a stateless location service. This service continuously overwrites spatial keys directly in memory using a Redis geocluster, bypassing disk writes for this ephemeral data. By separating the data, relying on Postgres for durable order states and in-memory Redis for volatile courier locations, the system prevents its hottest data path from impacting core operations. When a restaurant confirms an order, a Kafka event triggers the dispatch service. It queries the Redis geocluster to find all online drivers within a specific radius of the kitchen. It is a common assumption the system simply assigns the order to the closest driver. a nearest neighbor approach leaves significant optimization opportunities on the table. This visual represents the mixed integer program used by the dispatch optimization model. It calculates a multivariable cost matrix, weighing driver distance against kitchen prep time predictions and live traffic speed profiles. Crucially, it evaluates batching opportunities. The system calculates the route expansion delta to see if a courier can pick up a second order from a nearby restaurant without breaching the delivery window for the first customer. Because hundreds of dispatch workers run this logic simultaneously, the system uses Redis fencing tokens to establish distributed locks. This ensures two workers cannot assign the same order to two different couriers. Dispatch relies on continuous mathematical routing optimization. It calculates millions of permutations to solve for fleet efficiency, driver utilization, and food quality simultaneously. Once the courier picks up the order, the customer opens the app to watch the live delivery progress on a map. This comparison shows why traditional HTTP polling fails. If millions of customers asked the server for their courier's location every second, it would trigger a self-inflicted denial of service attack. Instead, the architecture uses order-scoped channel isolation. A persistent WebSocket connection is opened between the client and the tracking service, pushing location updates to the phone only when new data arrives. Because couriers only ping their location every 5 seconds, the client application performs coordinate interpolation. It uses heading and speed vectors to glide the map icons smoothly between coordinates, eliminating map jitter. WebSocket connections and client-side rendering deliver the illusion of continuous movement while optimizing server resource consumption. This diagram reveals the fully assembled architecture. Orange edge gateways route traffic, green microservices handle logic, the purple Kafka bus streams events, and yellow databases store data. During traffic spikes, Kafka buffers the shock, allowing the system to auto-scale microservices and clear the backlog. Planetary scale systems succeed by isolating transactional consistency from high-throughput location streams. The user interface provides the convenience, but it is this hidden lattice of data infrastructure that actually navigates the laws of physical logistics. Successfully merging distributed mathematics with real-world logistics is ultimately what allows these platforms to exist.